Hello, lovely humans. Jen Foxbot here for another exciting edition of Math Mondays, and we are going to continue our study of electrodynamics. Woo! In other words, the mathematical theory of electricity. Ooh, yeah. Okay, so in the last episode, we looked at the gradient, which is this fun little vector right here. I affectionately will probably refer to this mostly as del, because that's what the Greek letter is. I like to be lazy. So in the last episode, we looked at where this definition comes from. And in this episode, we're going to look at two things that we can do with del that are super, super helpful, both in electrodynamics, in physics in general, and in engineering. It popped up all the time. I was like, oh, this is handy. So the divergence and curl are important because they are tools that we can use to understand how different vectors are behaving. And electricity we often represent as perhaps a vector. A lot of things in electricity can be vectors because we can think about it as a thing that's moving with some amount of magnitude and a direction. So divergence and curl help us to better understand vectors. All right, so what are they? Okay, so the divergence is the dot product of del with a vector v, which we would write this way. I'm going to swap out the x hat, not swap out, I'm going to just move the unit vectors over so that we can better calculate the dot product. So we're going to get the partials like this, ddy plus z hat ddz dot vx x hat plus, whoopsies, the y is way too big, vy y hat plus vz z hat. And you're like, wait, hold on, what is this vx shenanigans? Okay, so really quickly, those are just the components of x in the respective directions. So for example, if my vector was like this, v, if I were to draw a line down to the bottom, where this is x, this is y, and this is z, this would be vy, this would be vx, or it could also be here too, and then this would be vc, or technically I guess this also would be vz. So basically just the components of the vector in that particular direction only. Okay, so when we do the dot product, we are going to get dvx, I should say what these actually mean, the partial derivative of the x component plus the partial derivative of the y component plus the partial derivative of the z component. And the key thing to note here is that this is a scalar, which is really interesting. So we take two vectors and we get a scalar. Boom, the dot product. Okay, that's cool and all, but like, why does this matter? Okay, well, we are going to get a scalar number that tells us how much the vector v spreads out at that particular point. So for example, let's say we get a divergence that looks something like this, where we have tiny little arrows, and then bigger arrows, and then way bigger arrows. Woo! So fun. Oh, whoops, my arrow got a little funky there. Okay, so you can kind of think about this like if I was at a pond or some sort of body of water, and I happen to have some pine needles in my pocket because Pacific Northwest forest, there's lots of them on the ground. I pick them up and I drop them in the water. And if I'm at a pond and they spread outward radially, I'm like, ooh, the water's moving. It's diverging from that point. So in this case, if they spread outward, the dot product is said to have a positive divergence. If they spread inward or kind of get sucked in, then we say that the divergence at that point is negative. So if you imagine the arrows were flipped and pointing inward, that would be negative. This is also called a source. And in the negative direction, they're called a sink. So another divergence that is non-zero might look like this. Uh-oh, we're running into the equation. Also, my arrows are great. so we have the arrows small at the bottom, and they're getting larger. So in this case, this kind of looks like a river, perhaps. So I drop my pine needles in, and they go shoo. And the farther away from me they are, the faster they start to go. I'm like, oh, okay, the water's moving in that direction. Again, a positive or non-zero divergence. But if you have a divergence that can be drawn like this, okay, we're just gonna try to do my best here. So imagine that these arrows are all equal lengths. Then you could say that, well, you would find, I guess I don't really need that, the divergence is 0. And so this would be if I was on a hot summer day in a very small pond, I drop my pine needles in, and nothing happens. Or maybe they all kind of float around aimlessly, but there's no clear direction. There's no preferred direction. So in this case, the divergence is 0. All right, so let's look at a specific example. Because usually we're not going to have a body of water, we're going to have an equation, and we're going to need to understand how to read that equation. Well, 1, how to calculate the divergence, and 2, how to read the equation. Okay, so let's say that we have a vector v that's like this, plus y hat, plus z hat. You also could think about this as the radial vector r, which is basically just if you have the equation y equals x, this is basically that, but in 3 dimensions. So let's calculate the divergence. Yes! Okay, so I'm not going to redraw this. We're just going to take this equation and be like, okay, the partial derivative of x with respect to x plus the partial derivative of y with respect to y plus the partial derivative of z with respect to z. Oh, look at that. It's just 1 plus 1 plus 1 equals 3. Cool. So we got a positive divergence. Woo! So you might notice, you're like, okay, it's a scalar. I don't really have a direction. Is it all pointing in one direction? Is it pointing radially outward? So for that, you'll need to know some information about v. But one thing that we can tell is, let's say we have another vector. We'll call it vb. We'll call that va. That looks like, hold on, let me make sure. Okay. We're gonna say that it's z hat. So in this case, VB would look something like this, where we have VB. The thing to note is that the magnitude of this vector changes as you get farther from the origin. So, cool, okay. So then we can calculate the dot product with del and v, and that's 0, that's 0, that's 1, equals 1. Okay, so this is interesting. So now we can start to say, okay, well, the divergence of this vector has a higher magnitude than this one. Ta-da! And lastly, let's say we have a vector c, which equals just 2z hat. So in this case, it's still a vector, but, I'm gonna pick a different color. I always forget to use these. Okay, so it's still a vector. It has a magnitude of 2 and a direction in the z direction, but the key difference between these two is that this vector c is always length 2. No matter where we are in our mathematical 3-dimensional space, the magnitude of this vector never changes. Okay, so now what happens if we try to find the divergence? Oh, okay, well this goes to 0, there's no components in the x or y direction, but the partial of a constant, the derivative of a constant, is 0. Oh, boom! Look at that! There's no divergence. Dun-da-da! Okay, so that makes sense once we understand what the divergence is. Basically, how much the vector is spreading out at that given point. This vector never changes. It doesn't spread out at all. So there's no divergence. Done. QED. Okay, cool. So that's divergence. I'm going to erase this, but we're going to keep this cute little picture here. We're going to erase the dot product. Cool. Okay, now we have the curl. And if you know much about vector stuff, it's a very technical term, stuff, you might be expecting this. The curl is defined as the cross product with a vector. Ooh, fun. Okay, so this one, I never remember the actual equation, so I like to draw it out. So you put your unit vectors up here, and then you put the components of your first vector here. So in this case, it's the partials, d, dy, d. Ooh, that's a funky looking dvz. And then you put your components of the second vector here. So we have vx, vy, and vz. Okay, and so this is how I remember it. So if you start with the unit vector, x hat, and I like to cover it so I know that I'm ignoring it, and you do these together, dot product of these two components together, so we're going to get dvz dy minus dvy dz. So it's these two and then minus these two, and then we add plus y hat, and we cover this one, and this one's opposite, so we do these two together. So dvx of dz minus dvz of dx. Let me just double check that because it's been a while. Yeah, cool, boom. Okay, plus z hat, and then we cover that one up, and then we do these two, the diagonals like that. Whoa, my parentheses backwards, holy moly. Okay, dvy dx minus dvx over dy. Okay, boom. Whew. That's some serious cross-producting. Okay, but what I want you to take note is that this is a vector. Boom. Magnitude and direction. Very cool, very cool. Okay, so this is known as the curl, and I'm going to get another color because I can. Oh, that's supposed to be an L, not an exclamation point. Okay, there we go. Okay, so the curl tells us how much our vector v, well, curls around a particular point. So instead of my pine needles, this time I grab a stick, I drop it in the water, and I notice that the stick is rotating. Oh, hey, that's curl. So the curl might look something, okay, the curl's really hard to draw. The curl might look something like this, where you have like kind of small vectors in the center, and then they get larger on the outside. I am so sorry to all of you lovely artists. My arrows are not at all in with the right viewpoint, but just imagine, use your imagination. Cool that they're all swirling around the origin. Yeah, small arrows in the middle, and they get larger as you go outward. You also might end up with something like this, where you have little arrows here, but in the opposite direction, and then they get larger as you go out. Whoa, so large! So large! Okay, they're not that large. Okay, and then they get large. Yeah, boom. Okay, so this scenario, I think this is Z. We'll call that Y for funsies. So this scenario is basically like if you have the escalator rails. Have you ever seen those videos where the people are really rigid and you put your body in the center? In one direction, the top of your body gets pushed in this direction, and the bottom of your body gets pushed in that direction, so you end up rotating. That's curl. Boom. So silly. See, there are real world connections everywhere. Good times. So yeah, but in this case, it might be more like a whirlpool. Boop. Okay. So, okay. So now let's do an actual example. I'm like, where am I in my notes? I got so excited about the escalator thing. Okay, so let's use these as an example, and let's say that this vector v, can y'all see that? Okay, that this vector v equals negative y in the x direction plus x in the y direction. And call that be a, because we're going to do 2. So now we're going to calculate the cross product, but whew, we're not going to do all this because we already have our equation here, no problem. We like to be lazy. Okay, so the first thing, let's be lazy. there are no components in the z direction, so all of the VZs go to 0. So that's 0, that's 0. Cool. And because we don't have any variables of z in this equation, so no components in the z hat direction, and z doesn't show up at all, so any derivative with respect to z is going to be 0. Boom. So right away we can knock, so this is going to 0 and that's going to 0, and now that and that can go to 0 as well. So all we're left with are the components in the z direction. The derivative of the y component with respect to x is going to be dx minus the derivative of the x component in the y direction. And since we already did this, I'm just gonna do it. Okay, so that's just 1, and the partial derivative of the x component with respect to y is just -1, but it's a minus, so we have 1 plus 1 equals 2 z hat. Woo! Yeah, party time. Okay. So this tells us that our curl has a magnitude of 2 in the z direction, and this is fun for all you lovely folks who remember the right-hand rule. If you're familiar with the right-hand rule, you curl your hand in the direction of the vectors, and your thumb points in the direction that the vector is pointing. Okay, so yeah, boom, just like we would expect. Okay, so now let's do this one, and let's say that this is represented by a vector b, where we're gonna say that this is x, y hat, and so now we do the curl of VB, and again in this case a lot of these things are going to go to 0. Woohoo! So no z components and no z variables, so both of these go to 0 again, and we end up with a z hat. The derivative of the y component with respect to x is just 1. The derivative of the x component with respect to y is 0, because there is no x component, so we go, whoops, I should do minus them, equals z hat. That's very cool. Okay, and again, oh, mine would be negative, wouldn't it? I was like, wait a second, it's gonna be that way. Okay, that's cool. I drew mine opposite to the book, so boom, we're just gonna have a little negative sign. Classic, I do that all the time. So in this case, you could think about placing a stick here, and you would rotate this way. And so then you would go, whoa, it's in the negative z direction. Oh yeah, boom. Throw my chalk on the ground. Okay, cool. So we covered a lot. We did a little bit of a review in vector component and a review in dot product and curl. Dot product and vector product. I would hope we covered the curl because I put it up there. So let me know if you have any questions about some of the vector math that's behind here. I also didn't really cover partial derivatives. I'm assuming you know some about that, but if you have any questions about that, I'll point you to some resources. And yeah, stay tuned for next week as we continue our exploration of electrodynamics. Woo! All right, have a good night, everybody. See you soon. Bye.